The morning of July 27th, 1944, began with what had become routine at Hollandia airfield in Dutch New Guinea. 16 P-38 Lightnings roared down the steel matting runway, their twin Allison engines screaming in perfect synchronization. The mission was straightforward on paper: Escort B-24 Liberators to strike Japanese positions in the Halmahera Islands, then return home. The distance was 1,280 miles, the longest fighter escort mission anyone had ever attempted in the Pacific theater. Captain Warren Lewis, flying lead in the 433rd Fighter Squadron, watched his fuel gauges with the same nervous attention every P-38 pilot had developed over the past year. The math was tight. Impossibly tight, actually. Standard operating procedures said this mission couldn't be done. The P-38's official combat radius was 570 miles. They were about to fly more than twice that distance, but something had changed in the previous 4 weeks. Something that headquarters in Brisbane didn't quite understand, and that Lockheed's engineers in Burbank flatly refused to believe. The P-38 pilots of the 475th Fighter Group had learned to fly their fighters in a way that seemed to violate every principle of aviation engineering. They were cruising at higher speeds, using less fuel, and returning from missions with tanks that should have been bone dry hours earlier. The technique came from a civilian, a 52-year-old technical representative who'd shown up at their base in June with a toolbox, a notebook full of calculations, and a reputation that preceded him by 17 years. His name was Charles Lindberg, and he was about to prove that everything the Army Air Force had been teaching its pilots about engine management was catastrophically wrong. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching. From today, the story of how one man's backwards fuel mixture made the P-38 Lightning into a completely different aircraft begins not in New Guinea, but 8,000 miles away in the frozen skies over England, where another group of P-38 pilots was discovering that their supposedly superior fighter was failing in ways nobody had anticipated. December 20th, 1943. 8th Air Force Headquarters at High Wycombe received yet another after-action report that made the statistics impossible to ignore. The 55th Fighter Group had launched 48 P-38 seconds that morning to escort bombers to Bremen. 31 had aborted before reaching the target. Not from enemy action, not from mechanical failure in any conventional sense. They were overheating at 40,000 feet in December in northern Europe, where ambient temperatures hovered around negative 40 degrees Fahrenheit. The numbers told a story that made no sense. November had seen abort rates around 15%. By mid-December, that figure had doubled. On deep penetration missions, where bomber streams spent hours above 35,000 feet, abort rates touched 50%. The P-38 groups were combat ineffective at precisely the altitudes where they were most desperately needed. Meanwhile, in the Pacific, a different problem was killing pilots just as efficiently. 5th Air Force P-38 seconds had the range advantage over Japanese fighters, but not enough range to reach the targets that mattered. Pilots were ditching in the Solomon Sea, running out of fuel 80 miles from base after missions that should have been within their operational radius. Mission planners in Brisbane spent their nights hunched over maps with rulers and protractors, measuring distances and calculating wind speeds, ultimately scratching off targets that sat just beyond the mathematics of fuel consumption. 2 theatres, 2 completely different problems. What nobody realized was that both issues stemmed from the same fundamental misunderstanding about how the Allison V1000 710 engines actually worked. The P-38 Lightning was supposed to be America's aerial equalizer. Kelly Johnson's masterpiece design solved the Army Air Corps' seemingly impossible specification from February 1937. A fighter that could reach 360 miles per hour, climb to 20,000 feet in 6 minutes, and maintain controllability at altitudes where most engines quit. The twin-engine configuration was elegantly radical. 2 Allison V-1710 engines mounted in separate booms, delivering combined horsepower that no single power plant could match. A central nacelle that positioned the pilot perfectly between the engines with ideal weight distribution. Forward firepower concentrated in the nose, one 20mm cannon and four 50 caliber machine guns, all firing through the propeller arc without synchronization gear. When the P-38 prototype first flew on January 27, 1939, it shattered expectations. Lieutenant Ben Kelsey pushed it to 413 miles per hour during speed trials, faster than any American fighter had ever flown. The Army ordered production before the prototype even finished its evaluation program, but every test flight, every validation trial, every performance evaluation happened in Southern California. Lockheed's test pilots took the P-38 up from Burbank, where the elevation sits at 775 feet above sea level. They pushed it through high-altitude trials over the Mojave Desert and the Sierra Nevada mountains, but they always returned to Burbank. The Army's acceptance flights at March Field followed the same pattern. What nobody realized was that California testing was fundamentally unrepresentative of combat conditions. Test flights lasted 90 minutes, maybe 2 hours maximum. Combat missions over Germany required 4 to 5 hours at sustained high altitude. Test flights involved steady climbs to altitude, followed by controlled descents. Combat missions meant rapid altitude changes, diving to engage fighters, climbing back to escort altitude, repeating that cycle multiple times while the engines worked at maximum continuous power. The engines themselves were marvels of engineering. Each Allison V1710 produced 1,425 horsepower. 12 cylinders arranged in a V configuration, liquid-cooled, equipped with General Electric turbo superchargers that allowed them to maintain sea-level power ratings all the way up to 25,000 feet and beyond. The Army Air Force's operating manual for the P-38 specified exactly how pilots should fly the aircraft. For cruise conditions, the manual called for high RPM and moderate manifold pressure, 2,300 to 2,400 revolutions per minute with 22 to 24 inches of mercury manifold pressure, auto-rich fuel mixture for safety and reliability. These settings came straight from Allison's engineering specifications and Lockheed's test data. Every pilot trained on these procedures. Every flight instructor taught them. Every technical order reinforced them. High RPM meant the engines were turning fast, which meant exhaust strokes were frequent, which meant cylinder pressure was quickly relieved. Moderate manifold pressure kept combustion temperatures under control. Rich fuel mixtures provided a safety margin against detonation and kept cylinder head temperatures in the green zone. It all made perfect sense. It was also systematically destroying the P-38's combat effectiveness in ways that nobody understood. The problem in Europe was thermal. Those pure ethylene glycol cooling systems that worked flawlessly in California were boiling over at altitude because atmospheric pressure dropped and brought the coolant's boiling point down with it. At 38,000 feet, ethylene glycol boiled at around 240 degrees Fahrenheit. The engines were running cylinder head temperatures between 230 and 250 degrees. The coolant was literally boiling inside the engine, creating vapor pockets that insulated hot metal surfaces instead of cooling them. The system spiraled into catastrophic overheating in minutes. Technical Sergeant Anthony Bengalas at the 82nd Air Depot Group in Langford Lodge, Northern Ireland, solved that problem in February 1944 with a 70-30 mixture of water and ethylene glycol. Water's superior specific heat capacity of 1.0 BTU per pound per degree Fahrenheit compared to glycol's 0.57 meant the mixture absorbed nearly twice as much heat energy. Cooler cylinder heads meant less risk of exceeding the boiling point, even though that boiling point was technically lower. Bengala's modifications spread through unofficial channels by late February. Crew chiefs talked to other crew chiefs. By March, an estimated 60% of 8th Air Force P-38 seconds were running the modified coolant. The 22nd mission to Berlin on March 3rd put 48 P-38 seconds from the 55th Fighter Group over the target area at 39,000 feet. Every single one of them stayed with the bomber stream. 0 aborts for overheating. But solving the cooling problem in Europe did nothing to address the fuel consumption problem in the Pacific. And that's where Charles Lindberg entered the story. In June 1944, Lindberg arrived at Hollandia airfield as a civilian technical representative for United Aircraft Corporation. Officially, he was there to evaluate twin-engine fighter performance under combat conditions. Unofficially, he was there because he'd heard that P-38 pilots were dying from fuel exhaustion faster than they were dying from Japanese fighters. Lindberg had a particular expertise that nobody else in the Pacific Theater possessed. He understood long-range fuel management at a level that bordered on instinctive genius. His 1927 solo flight across the Atlantic had required him to nurse every gallon of fuel in the Spirit of St. Louis across 3,600 miles of open ocean. He'd spent the following decade working as a technical advisor to Pan American Airways, optimizing fuel consumption for their long-range flying boats. When he showed up at the 475th Fighter Group's operations tent and introduced himself to Colonel Charles MacDonald, the group commander didn't quite catch his name at first. MacDonald was in the middle of a checker game. Lindberg explained that General Donald Hutchinson had sent him over to discuss combat operations of the P-38. MacDonald's response was polite but skeptical. "We're flying these things as efficiently as we can. The manual says 2,300 RPM, 24 inches manifold pressure, auto-rich mixture. We're following the book." Lindberg's reply changed. "Everything. That's your problem. You're following the book." The next morning, June 26, 1944, Lindberg flew his first combat mission with the 475th. He'd checked out in the P-38 only a few days earlier, borrowing Richard Bong's old aircraft to fly to Hollandia. Major Thomas Maguire, America's second highest scoring ace, led the mission. Lindberg flew on Maguire's wing. The target was a Japanese shipping concentration at Wardo Bay. The flight took off at 10:30 in the morning, 6 P-38 seconds climbing to 15,000 feet for the long run north. The mission profile called for 6.5 hours of flight time. Standard fuel load, standard mixture settings as specified in the manual, except Lindberg wasn't using standard settings. MacDonald had authorized him to experiment, partly out of curiosity and partly out of desperation. The group's operational radius was constrained by fuel, and every mission planner knew they were leaving valuable targets unattacked because the P-38 seconds simply couldn't reach them and make it home. Lindberg set his engines to 1,600 revolutions per minute. He adjusted his manifold pressure to 30 inches of mercury. He moved his mixture controls to auto-lean. Every setting was backwards according to the manual. Low RPM meant fewer exhaust strokes, which meant cylinder pressure stayed elevated longer. High manifold pressure meant more air was being forced into the cylinders, which meant higher combustion temperatures. Lean fuel mixture meant less fuel cushion, which meant increased risk of detonation. By every principle the Army Air Force taught, Lindbergh's engines should have started detonating within minutes. Pistons should have melted. Cylinder heads should have warped. The aircraft should have been trailing smoke before they even reached the target. Instead, something remarkable happened. After 6.5 hours of flight time, MacDonald and the other pilots landed with their fuel gauges showing the normal minimum reserve. Maybe 35 to 40 gallons remaining. Enough for 25 minutes of emergency flight time if you were lucky. Lindberg landed with 210 gallons still in his tanks. Enough for nearly 2 more hours of flight. The ground crew chief checked the fuel load 3 times, convinced his measuring sticks were wrong. They weren't. Lindberg had flown the exact same mission profile as everyone else, fought in the same combat engagement, and returned with 6 times more fuel than his wingmen. MacDonald called an assembly that evening at the recreation hall. Palm, thatched roof, dirt floor, 1 ping-pong table, unshaded light bulbs. Under that harsh lighting, Lindberg explained to the pilots of the 475th Fighter Group why everything they'd been taught about flying the P-38 was wrong. The physics behind Lindberg's technique weren't complicated, but they contradicted 15 years of aviation doctrine. The Army Air Force had built its engine management procedures around a principle called square power settings, where manifold pressure in inches of mercury matched RPM in hundreds. 23 inches and 2300 RPM, 24 inches and 2400 RPM. This was considered the safe, proven way to operate piston engines. The logic seemed sound. High RPM meant the engine was spinning fast, which meant each power stroke was brief, which meant peak cylinder pressures didn't last long enough to cause damage. Moderate manifold pressure kept combustion forces manageable. The combination was supposed to balance power output against engine longevity. But square power settings created a fundamental inefficiency that nobody had bothered to calculate. High RPM meant high internal friction, pistons sliding up and down at 2400 strokes per minute, connecting rods articulating at extreme speeds, crankshaft bearings working against tremendous rotational forces. All of that, friction consumed power that had to be generated by burning fuel that wasn't contributing to forward thrust. Lindberg understood something that the Army's engine management doctrine had missed. Friction increases with the square of velocity. Double the engine speed, and you quadruple the friction losses. An engine spinning at 2400 RPM was using dramatically more fuel just to overcome internal resistance than the same engine producing the same power at 1600 RPM. The manifold pressure side of the equation was equally misunderstood. Low manifold pressure meant the turbochargers weren't working hard. The compressed air entering the engine was relatively cool, which meant it went through the intercoolers and arrived at the intake manifold even cooler. Cold air entering cold engines created problems with fuel vaporization. Some of the gasoline wasn't burning efficiently. It was pooling in the intake manifold as liquid, creating rich spots and lean spots in the combustion chambers. Lindberg's backwards settings solved both problems simultaneously. 1600 RPM meant the engines were turning slowly enough that friction losses dropped by roughly 40% compared to 2400 RPM operation. That alone saved fuel. But the real genius was in the manifold pressure increase. 30 inches of mercury meant the turbochargers were spinning faster, compressing more air, generating more heat through compression. That warmed air still went through the intercoolers, but it arrived at the intake manifolds warm instead of frigid. Warm manifolds meant better fuel vaporization. Better vaporization meant more complete combustion. More complete combustion meant more power extracted from each gallon of fuel. The lean mixture setting was the final piece of the puzzle. Auto lean meant the engine was running with just enough fuel to maintain combustion, no excess for cooling. At first glance, this seemed dangerous. Rich mixtures provided a temperature buffer. Lean mixtures ran hotter and risked detonation if combustion pressures exceeded the fuel's octane rating. But here's what Lindberg understood that the manual writers didn't. The Allison V1710 was designed with significant safety margins. Its compression ratio of 6.65 to 1 was conservative compared to some European engines. The 100-octane fuel the Americans were using had detonation resistance far beyond what the engine actually needed at cruise power settings. Running lean at 1600 RPM and 30 inches didn't push the engine anywhere near its detonation threshold. It just eliminated the wasted fuel that rich mixtures were dumping through the cylinders as insurance against problems that weren't going to happen. The night of June 26th, MacDonald gathered his squadron commanders to discuss Lindberg's demonstration. The room divided immediately into two camps. The believers saw the fuel consumption data and he wanted to adopt the new techniques immediately. The skeptics worried they were about to destroy dozens of engines based on one flight by a civilian who'd never flown a P-38 inches combat before last week. Captain Robert Wilson, the engineering officer for the 39th Fighter Squadron, was in the skeptical camp. He'd read the Allison technical manuals. He'd attended the engine maintenance schools. Everything in his training said that low RPM and high manifold pressure was a recipe for detonation and engine damage. But Wilson was also a pragmatist. He proposed a compromise: run a controlled test, take 6 aircraft on a long-range mission, 3 flown using standard settings, 3 using Lindberg's technique, monitor cylinder head temperatures, oil pressure, manifold pressure, and fuel consumption throughout the flight. If the modified aircraft showed any signs of detonation or overheating, abort the experiment immediately. MacDonald approved the test for June 28th. The mission was an armed reconnaissance to Japanese airfields on Seram Island, roughly 400 miles north of Hollandia, 6 P-38 seconds, divided into 2 flights of 3. Flight A would use standard power settings. Flight B would use Lindberg's technique. Lieutenant James Watkins led Flight A. He was by the book in everything, which made him perfect for the control group. He set his engines to 2300 RPM, 23 inches manifold pressure, auto-rich mixture as the manual specified. Lindberg led Flight B. He was flying with 2 other pilots who'd volunteered for the experiment, both of them young enough that following a civilian's advice over Army doctrine didn't trigger their institutional resistance. The flights took off at 0630 and climbed to 15,000 feet. The first hour was routine. Both flights maintained formation, watching their instruments, comparing notes over the radio. Watkins reported his fuel consumption at 82 gallons per hour, exactly what the manual predicted for their power settings and altitude. Lindberg reported 70 gallons per hour, 12 gallons per hour less, which over a 6-hour mission would translate to 72 gallons saved. 72 gallons was nearly 2 hours of additional flight time. But fuel consumption numbers alone didn't prove anything. The real test was engine health. Were Lindberg's engines running hotter? Were they showing signs of stress that would lead to failure? Wilson was monitoring from the operations tent, listening to radio reports and plotting the data on graph paper. Watkins' flight reported cylinder head temperatures around 205 to 210 degrees Fahrenheit, normal for their power settings. Oil pressure steady at 70 to 75 pounds per square inch. No anomalies. Lindberg's flight reported cylinder head temperatures around 220 to 225 degrees Fahrenheit, 15 degrees hotter than standard operation, but still well within the engine's designed operating range. Oil pressure was slightly higher, 78 to 80 psi, which actually indicated better lubrication at the lower RPM. No detonation, no rough running, no signs of distress. The mission lasted 5 hours and 40 minutes. Both flights engaged in strafing runs on Japanese positions, which meant full throttle operation for brief periods. They encountered no enemy fighters, which meant no high-speed combat maneuvering that would have provided an extreme stress test. When they landed, the fuel consumption data was decisive. Watkins' flight averaged 84 gallons per hour over the mission, slightly higher than crew's because of the combat maneuvering. They landed with an average of 32 gallons remaining. Lindberg's flight averaged 71 gallons per hour. They landed with an average of 105 gallons remaining, 3 times more fuel than the control group. Wilson spent that evening tearing down one of the engines from Lindberg's flight. He pulled the cylinder heads, inspected the pistons, examined the valve seats, checked for any signs of detonation damage or thermal stress. He found nothing. The engine was in perfect condition. If anything, it showed slightly less carbon buildup than engines that had been running rich mixtures. By June 30th, MacDonald had made his decision. Every pilot in the 475th Fighter Group would be trained on Lindberg's fuel management technique. The transition would begin immediately. The training sessions started that afternoon. Lindberg stood in front of 30 pilots and walked them through the procedure step by step. Set RPM to 1600 during climb-out. Once established in cruise at altitude, advance manifold pressure to 30 inches. Move mixture controls to auto-lean. Monitor cylinder head temperatures. They should settle between 220 and 230 degrees. If temperatures exceed 235, enrich the mixture slightly. If they stay below 215, you can lean further. The pilots had questions. What happens if we need combat power suddenly? Won't the engines be sluggish, responding from such low RPM? Lindberg's answer was based on physics, not theory. The turbochargers are already spun up because of the high manifold pressure. When you advance the throttles and increase RPM, you'll have instant power response, faster than you would from high RPM and low boost, because the turbos won't be lagging. What about engine wear? Won't low RPM and high cylinder pressure cause problems? The opposite. Lower RPM means less friction, which means less wear on bearings and piston rings. The cylinder pressures aren't actually higher. You're just extracting more useful work from each combustion event instead of wasting it as heat and friction. What if one engine fails? Won't low RPM make it harder to maintain altitude on one engine? Actually, no. You'll have more power available from the remaining engine because it's running more efficiently, and you'll have more fuel to work with, which means more time to get home. The pilots absorbed the information with varying degrees of enthusiasm. The younger ones, the lieutenants who'd been in theatre for less than 6 months, accepted it easily. They hadn't flown long enough for the old techniques to become deeply ingrained habits. The older hands, the captains and majors who'd been flying P-38 seconds since 1942, had more difficulty. Unlearning 15 years of aviation doctrine wasn't easy, but the fuel consumption numbers were impossible to argue with. And over the next 2 weeks, as more missions were flown using Lindberg's technique, the evidence became overwhelming. On July 3rd, the 433rd Fighter Squadron flew an escort mission to Manokwari, 620 miles from base. Previously, that distance had required careful fuel management and had left pilots landing with minimum reserves. Using Lindberg's technique, they completed the mission and landed with an average of 90 gallons remaining, enough fuel to have flown another 150 miles if needed. On July 9th, a mixed formation of P-38 seconds and B-24 seconds attacked Japanese shipping at Amboina. The round trip was 800 miles. 3 P-38 seconds using standard power settings had to divert to an emergency strip at Biak Island because they were critically low on fuel. The 12 P-38 seconds using Lindberg's technique all made it back to Hollandia with fuel to spare. On July 15th, a reconnaissance mission to Halmahera Island pushed the P-38's theoretical range to its absolute limit, 900 miles from base. The mission was approved only because every aircraft was using the new fuel management protocol. All 6 P-38 seconds completed the mission and returned with an average of 65 gallons remaining. The cumulative effect of these missions was transforming the strategic calculus of the Pacific War in New Guinea. Targets that had been unreachable were suddenly within range. Japanese airfields that had operated with impunity because they were beyond fighter escort range were now vulnerable. The P-38's effective combat radius had expanded from 570 miles to somewhere between 750 and 800 miles. General George Kenney, commanding the 5th Air Force, heard about the fuel consumption improvements through the informal network of pilots and maintenance officers. By mid-July, stories about the civilian who was teaching pilots to fly backwards were circulating through every P-38 unit in theatre. Kenney summoned Lindberg to 5th Air Force headquarters in Brisbane on July 18th. The meeting was partly to legitimize Lindberg's presence in the combat zone. He was technically there without proper authorization from Southwest Pacific Command, and partly because Kenney wanted to understand exactly what was happening with his P-38 groups. Lindberg explained the technique. Kenney, who'd started his career as a pilot in World War I and understood engines at a fundamental level, grasped the physics immediately. "This is basic thermodynamics," Kenney said. "Why didn't Allison tell us this? Why didn't Lockheed include it in the operating manual?" Lindberg's answer was diplomatic but pointed. They tested the aircraft for safety margins, not for optimal efficiency. The high RPM settings are safe under all conditions, even poor maintenance, even low-quality fuel, even pilot error. What I'm teaching requires more pilot discipline and better engine monitoring. It's optimal, but it's not foolproof. Kenny made a command decision. Lindberg would spend the next month visiting every P-38 unit in the Southwest Pacific, teaching the technique to every pilot and every crew chief. The fuel savings weren't just tactical, they were strategic. Every gallon of fuel saved was one less gallon that had to be shipped across the Pacific from California. The logistics tail for 5th Air Force stretched 8,000 miles. Anything that reduced fuel consumption by 20 to 30% was worth implementing immediately. The training program expanded rapidly. By late July, Lindberg was conducting sessions at multiple bases. He'd spend mornings in the operations tent explaining the theory, afternoons flying demonstration missions, evenings debriefing with maintenance officers about engine monitoring procedures. The technique spread beyond the 475th Fighter Group. The 49th Fighter Group adopted it in early July. The 475th Fighter Group's kill rate, which had always been impressive, improved noticeably because pilots could stay in combat zones longer without worrying about fuel. The 8th Fighter Group, which had been restricted to shorter-range missions because of fuel concerns, suddenly found themselves able to escort bombers to targets they'd previously considered unreachable. But not everyone was pleased with the transformation. Allison Engine Company's field representatives started receiving reports that P-38 pilots were operating engines outside approved parameters. The reports triggered alarm bells at company headquarters in Indianapolis. Running engines at 1600 RPM and 30 inches manifold pressure violated the operating envelope that Allison had specified. The company sent urgent cables to 5th Air Force, warning that unauthorized operating procedures could void engine warranties and result in catastrophic failures. Lockheed's position was even more hostile. The P-38's flight manual was a carefully engineered document. Every power setting had been tested. Every procedure had been validated. Now, some civilian was telling combat pilots to ignore the manual and fly the aircraft in ways that Lockheed had never approved. The company's legal department started preparing documentation that would absolve Lockheed of responsibility for any engine failures that resulted from unauthorized operating procedures. 5th Air Force's response to both companies was brutally simple. The technique works. The data proves it. If your manuals are wrong, that's your problem, not ours. By August 1st, 1944, roughly 80% of 5th Air Force P-38 seconds were being operated using Lindberg's fuel management technique. The operational impact was transforming the air war in the Southwest Pacific. The mission to the Halmahera Islands on July 27th demonstrated the full potential of the new operating procedures. 16 P-38 seconds escorted B-24 seconds to targets 1,280 miles from base. The round trip took 9 hours and 40 minutes, longer than any previous fighter mission in the Pacific theater. Every P-38 completed the mission. Average fuel remaining upon landing was 45 gallons. Before Lindberg's techniques, that mission would have been impossible. Pilots would have been ditching in the ocean, 200 miles short of home. Japanese intelligence officers noticed the change. They started receiving reports from airfield commanders that American P-38 seconds were appearing over targets that should have been well beyond fighter range. The Americans had somehow extended their combat radius without modifying their aircraft. Japanese tactical planning, which had relied on certain targets being safe from fighter escort, had to be completely revised. But the most dramatic demonstration of the technique's effectiveness came on July 28th, during a mission that officially never happened. Lindberg was flying with the 433rd Fighter Squadron on what was supposed to be a routine patrol along the northern coast of Seram Island. 8 P-38 seconds, standard combat air patrol, looking for targets of opportunity. Lindberg was flying as wingman to Colonel MacDonald, who'd become something of a friend over the previous month. At 14:20 hours, MacDonald's element spotted a Japanese Mitsubishi Ki-51 Sonya reconnaissance aircraft at 8,000 feet. The Sonya was alone, no escort, flying a photo reconnaissance mission over Allied positions. MacDonald called the bounce. His element rolled inverted and dove toward the Japanese aircraft. The Sonya pilot saw them coming and tried to run, diving toward the jungle canopy where he hoped the P-38 seconds size and speed would make them reluctant to follow. MacDonald pursued Lindberg on his wing. The Sonya was maneuvering aggressively, jinking through valleys, using terrain to mask his position. MacDonald got off several bursts but couldn't establish a solid firing solution. Then the Sonya pilot made a mistake. He pulled up out of a valley and entered a climbing turn, probably trying to gain altitude for better visibility. The maneuver left him exposed for perhaps 3 seconds. Lindberg was in position. He'd been flying perfect formation on MacDonald's wing, not participating in the attack, just observing. But now the Japanese aircraft was directly in front of him, climbing through his firing cone. The decision took less than a heartbeat. Lindberg pressed the trigger. The P-38's nose armament erupted. 4 50 caliber machine guns and 1 20mm cannon, all converging on the Sonya at 200 yards range. The Japanese aircraft shuddered under the impact. The left wing root exploded, fuel and hydraulic fluid mixing with cannon rounds. The Sonya rolled inverted and augured into the jungle, trailing black smoke. When they returned to base, MacDonald faced a problem. Charles Lindberg, civilian technical representative, had just shot down a Japanese aircraft in combat. He wasn't supposed to be flying combat missions at all, let alone engaging enemy aircraft. If word got back to headquarters, or worse, to Washington, the political ramifications would be severe. MacDonald's solution was pragmatic. The mission report credited the kill to his element. No names mentioned. Lindberg's participation in the mission was omitted from the official record. The gun camera footage was quietly filed away, but everyone at Hollandia knew what had happened. The civilian who was teaching them to fly their P-38 seconds more efficiently had just proved he could fight in them too. General Kenny heard about the incident 2 days later through the same informal network that had spread Lindberg's fuel management techniques. His response was immediate. Lindberg was ordered to cease all combat flying effective immediately. He could continue training pilots, but he was not to fly any more missions where contact with enemy forces was possible. Lindberg's time in the Pacific was coming to an end anyway. United Aircraft Corporation wanted him back in the States. There were other projects that needed his attention. The F-4U Corsair program needed optimization. The company's experimental jet engines required evaluation. On August 15, 1944, Lindberg departed Hollandia for the final time. He'd spent 2 months in the Southwest Pacific. He'd flown approximately 50 combat missions, though the official number was considerably lower because most of his flights were classified as observation or familiaration rather than combat operations. He'd shot down 1 Japanese aircraft, though that kill would never appear in any official record. More importantly, he'd taught an entire theatre's worth of P-38 pilots how to extract performance from their aircraft that Lockheed's engineers insisted was impossible. The fuel savings he'd introduced would persist for the rest of the war. Every P-38 pilot who flew long-range missions in late 1944 and 1945 benefited from techniques that Lindberg had demonstrated that summer. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The question that puzzled historians for decades afterward was simple. If Lindberg's technique was so effective, why wasn't it in the manual? Why had Allison and Lockheed specified operating procedures that were demonstrably less efficient than what one civilian discovered in a few weeks? The answer lies in how aircraft manufacturers approached engine testing in the 1930s and 40s. Safety was paramount. Engines were tested under worst-case conditions. High temperatures, poor fuel quality, inadequate maintenance, pilot error. The goal was to find power settings that would keep engines running under any circumstances. High RPM and moderate manifold pressure met that goal. Those settings were forgiving. A pilot could run his engines slightly too rich or slightly too lean, and the engine would tolerate it. Cylinder head temperatures would stay manageable. Detonation risks would remain low. The engine would keep running even if the pilot wasn't monitoring his instruments carefully. Lindberg's technique required precision. Pilots needed to watch their cylinder head temperatures constantly. They needed to adjust mixture settings based on altitude, airspeed, and ambient temperature. They needed to understand the relationship between RPM, manifold pressure, and engine efficiency. It wasn't difficult, but it required attention and discipline. The Army Air Force, training thousands of pilots under wartime pressure, had opted for procedures that minimized training time and reduced the risk of pilot error. Better to have slightly inefficient engines that were easy to operate than optimal engines that required expert management. That philosophy made sense for training and peacetime operations. But in combat, where fuel range meant the difference between completing a mission or ditching in the ocean, optimal efficiency mattered more than operational simplicity. What made Lindberg unique wasn't superior engineering knowledge. Allison's engineers understood thermodynamics just as well as he did. What made him unique was his perspective. He approached the P-38 not as a military aircraft with established procedures, but as a long-range flying machine where every gallon of fuel mattered. His 1927 Atlantic flight had taught him to think about fuel consumption at a level of detail that most pilots never considered. The Spirit of St. Louis had carried 450 gallons of fuel. Lindberg had burned approximately 410 gallons during the flight, landing in Paris with perhaps 40 gallons remaining. That 33-hour mission had required him to optimize every aspect of engine operation. He'd experimented with different RPM settings, different mixture ratios, different throttle positions. He'd learned that the engine's theoretical fuel consumption didn't match its actual fuel consumption if you were willing to operate it outside the manufacturer's conservative recommendations. That same mentality applied to the P-38. The Allison engines could do more than the manual said they could do if you were willing to monitor them carefully and operate them precisely. The Army Air Force never officially adopted Lindberg's techniques. No revised technical manual was issued. No updated pilot training program incorporated his fuel management procedures. The official stance remained that pilots should follow the existing operating manual. But in the Pacific, where results mattered more than procedures, Lindberg's techniques became standard practice. Pilots taught other pilots. Crew chiefs learned to recognize the sound of engines running at 1600 RPM and 30 inches, and they stopped writing up discrepancy reports when they heard it. Squadron commanders, who saw their operational radius expand by 200 miles, stopped asking questions about whether pilots were following the manual. By September 1944, when American forces landed on Morotai Island and began establishing forward bases closer to the Philippines, 5th Air Force P-38 seconds were routinely flying 9- and 10-hour missions. These flights would have been impossible 6 months earlier. The extra range meant better bomber escort coverage, more fighter sweeps over Japanese airfields, more reconnaissance missions into enemy territory. The tactical advantage was significant enough that Japanese commanders in the Philippines requested reinforcements specifically to counter the increased American fighter presence. Intelligence reports from late 1944 show Japanese officers expressing confusion about how American P-38 seconds were reaching targets that should have been beyond their range. The speed issue, the one implied in that provocative title about flying 60 miles per hour faster, requires a more nuanced explanation. Lindberg's technique didn't increase the P-38's maximum speed. The aircraft could still make approximately 420 miles per hour in level flight at 25,000 feet, same as always. But it changed the aircraft's effective cruising speed in ways that felt like a performance improvement to the pilots flying them. Here's why. Under standard operating procedures, pilots cruising at high RPM and low manifold pressure were typically flying at around 270 to 280 miles per hour. This was the speed that gave them maximum endurance, the slowest speed they could fly while still maintaining enough efficiency to reach their targets and return home. Lindberg's technique allowed them to cruise at 310 to 320 miles per hour, while using less fuel than the standard settings consumed at 270. The engines were more efficient at low RPM and high boost, which meant they could maintain higher speeds without penalty. The practical result was that mission times decreased even though the distances stayed the same. A flight that used to take 7 hours at 270 miles per hour now took 6 hours at 315 miles per hour. To the pilots, it felt like the aircraft had gotten faster. They were covering ground more quickly. They were spending less time in the air. Enemy fighters that used to be able to predict their arrival times were now finding American formations showing up 30 to 40 minutes earlier than expected. There was also a psychological component. Engines running at 1600 RPM sounded different from engines at 2400 RPM. They had a deeper, more powerful resonance. The higher manifold pressure meant the turbochargers were whistling at a higher pitch. Pilots reported that their aircraft felt more responsive, more energetic, even though the actual performance specifications hadn't changed. And there was the throttle response issue. When you're cruising at 1600 RPM and 30 inches manifold pressure, the turbochargers are already spun up and producing significant boost. If you need combat power suddenly, you can advance the throttles and increase RPM, and you get instant response. The engines jump from cruise to combat power in perhaps 2 seconds. Compare that to the old technique. Cruising at 2400 RPM and 22 inches meant the turbochargers were barely working. When you needed combat power, you had to wait for the turbos to spool up. There was a lag of 4 to 6 seconds before full power became available. In a dogfight, 6 seconds could mean the difference between getting your shot and getting shot. So, while Lindberg's technique didn't technically make the P-38 faster in terms of maximum speed, it made the aircraft more effective in every practical sense. Faster cruising speeds, better throttle response, longer range, more time in the combat zone, all from simply operating the engines the way they were actually designed to work rather than the way the manual said to work them. The Luftwaffe never figured it out. German intelligence officers analyzing American fighter performance in late 1944 and early 1945 noticed that P-38 combat radius had increased significantly, but they attributed it to modifications they assumed the Americans had made. Larger fuel tanks, more efficient engines, aerodynamic improvements. They never considered that it might be something as simple as different power management. Japanese intelligence came closer to understanding. Some post-war interrogations of Japanese fighter pilots mentioned that American P-38 seconds in late 1944 seemed to be flying at higher cruise speeds than earlier in the war. They noticed the change, but they didn't understand the cause. The British, who'd rejected the P-38 back in 1941 as unsuitable for European operations, heard about the fuel consumption improvements and requested detailed information from 5th Air Force. They were considering reintroducing Lightnings for long-range operations over Burma and wanted to know if the American techniques could be applied to their aircraft. The answer was complicated. British P-38 seconds had been delivered with different engine configurations. They lacked turbochargers, which meant they couldn't run the high manifold pressures that made Lindberg's technique work. The British would have needed to modify their aircraft significantly to match American performance. By the time the bureaucratic process of requesting modifications and funding them worked through British procurement channels, the war in Burma was winding down. The improved fuel techniques remained an American innovation, never widely adopted beyond 5th Air Force. Even within the American military, adoption was inconsistent. 8th Air Force in Europe continued to operate P-38 seconds using standard power settings through the end of the war. Part of this was institutional inertia. Part was because the cooling system problems in Europe had been solved by the water glycol mixture modification, and commanders saw no urgent need to change fuel management procedures on top of that. 13th Air Force in the South Pacific adopted Lindberg's techniques in September 1944 after hearing about the results in 5th Air Force. But their implementation was less systematic. Some squadrons used it, some didn't. Training was inconsistent. The fuel savings were real but not as dramatic as in 5th Air Force because pilots weren't as disciplined about monitoring their engine instruments. The most complete adoption happened in the Philippines campaign. When American forces invaded Leyte in October 1944, P-38 groups operating from Leyte and later from Luzon were flying missions that covered nearly the entire Philippine archipelago. These flights, some lasting 9 hours, were only possible because every pilot in theater had been trained on fuel management techniques that maximized efficiency. Major Richard Bong, America's highest-scoring ace with 40 confirmed kills, flew exclusively with Lindberg's power settings during his final combat tour in late 1944. Bong's combat reports from October and November mention fuel loads and consumption rates that clearly show he was running low RPM and high manifold pressure. The extended range let him hunt deeper into Japanese-held territory, contributing to his final kill total. Major Thomas Maguire, the second highest-scoring American ace, was even more aggressive about using the technique. Maguire had been one of the first pilots to adopt Lindberg's methods back in June, and he'd spent the summer training other pilots in his squadron. By the time he was killed in January 1945, he'd flown dozens of missions that would have been impossible under standard fuel management. Maguire's death, ironically, had nothing to do with fuel or engine management. He was killed when his P-38 stalled during a low-altitude dogfight while carrying external fuel tanks he'd forgotten to jettison. The added weight and drag made the aircraft uncontrollable at low speed. It was a pilot error, the kind of mistake that happens when you're focused on the fight and forget basic procedures. But the fact that Maguire was still carrying external tanks during a dogfight speaks to how much the fuel situation had improved. In early 1944, P-38 pilots dropped their external tanks immediately upon any sign of combat because they needed every advantage in maneuvering. By late 44, fuel was so much less of a constraint that pilots sometimes forgot they were carrying tanks. The range anxiety that had dominated Pacific operations for 2 years had essentially disappeared. The long-term legacy of Lindberg's work with the P-38 extended far beyond World War II. The principle he'd demonstrated, that manufacturer-recommended power settings weren't necessarily optimal power settings, influenced post-war engine development and pilot training. The jet age eliminated some of these concerns. Jet engines didn't have the complex relationship between RPM, manifold pressure, and fuel mixture that piston engines required. But the fundamental insight remained relevant. Optimal performance required understanding how engines actually worked, not just following the manual. When the Air Force developed its first jet fighters in the late 1940s and early 1950s, the flight testing programs included extensive evaluation of fuel consumption at various power settings. Engineers explicitly looked for the kind of efficiency gains Lindberg had discovered, trying to find operating regimes where the engines performed better than their nominal specifications suggested. Commercial aviation absorbed the lesson even more directly. Airlines in the 1950s, flying long-range propeller aircraft like the Lockheed Constellation and the Douglas DC-7, employed fuel management specialists who optimized engine settings for each route. These specialists used techniques directly descended from what Lindberg had taught P-38 pilots: low RPM, high manifold pressure, lean mixtures, constant monitoring of engine temperatures. The fuel savings for airlines translated directly into profit. A 1% improvement in fuel efficiency across a fleet of 50 aircraft flying 1 million miles per year meant tens of thousands of dollars in reduced fuel costs. Airlines that employed better fuel management had a competitive advantage over airlines that simply followed manufacturer recommendations. Modern general aviation still teaches the principle. Pilots learning to fly complex single-engine aircraft like the Beechcraft Bonanza or Cessna 210 are taught about the relationship between RPM and manifold pressure. The phrase over-square operation, running more manifold pressure than RPM, is standard terminology. Most flight schools teach it as the efficient way to cruise. Few of those pilots know that the technique traces back to a civilian flying combat missions in a P-38 over New Guinea in the summer of 1944. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.